Let's look at Coulomb's law. Coulomb's law is that the electric force, F sub E, is equal to K Q1 times Q2 over R squared. We'll take the absolute value of those charges, and then we'll look at the problem to determine the direction of the force. The electric force will be measured in newtons. The charge is measured in coulombs, and we use a capital C to represent coulombs. And distance will be in meters. The Coulomb's constant, or K, is 9 times 10 to the 9, and its unit is Newton meter square per Coulomb squared. As long as you're always using meters, coulombs, and newtons, you don't need to worry about adding the unit in your work. Let's solve a problem. 1 coulomb of charge is very large. So a 2 microcoulomb charge is at a distance of 1 centimeter from another 3 microcoulomb charge. What is the magnitude of the electric force between the two charged particles? First of all, notice that the charges are measured in microcoulombs. The micro symbol is a mu, similar to the coefficient of friction, but mu means times 10 to the negative 6. So this is just so Q1 could be written as a 2, and then we're going to replace micro with times 10 to the negative 6 coulombs. And then Q2, the other charge, will be 3 times 10 to the negative 6 coulombs. Now notice the distance is 1 centimeter. And remember, our distance needs to be in meters. So in this case, R is equal to 1 centimeter, but we need to convert it, and 1 centimeter is equal to 0.01 meters. So now that we've taken care of our conversions, we can solve our problem. So if the electric force is equal to the constant K, absolute value of Q1 times the absolute value of Q2, all over R squared, we can substitute in 9 times 10 to the 9 for K. Now both of these charges are positive, so our absolute value of Q1 times Q2 will just be 2 times 10 to the negative 6 times 3 times 10 to the negative 6. Then we're going to divide it by R squared, so that would be 0.01. Remember, we wanted in meters, and we had to do a conversion. After substituting, I get 540 newtons. Now, these two charges, being both positive charges, would repel each other. So if I had the positive 2 microcoulomb charge here, and then 1 centimeter away, this is our distance marker, we have the positive 3 microcoulomb charge, then the positive 2 microcoulomb charge would push the 3 microcoulomb charge away with this electric force that would be equal to 540 newtons. And then the 3 microcoulomb charge would push the 2 microcoulomb charge away with an equal force of Fe is 500 newtons. Now remember, Newton's third law tells us that for every force, there is an equal and opposite directed force between two bodies, and we have these two bodies applying an equal but opposite force on each other.